DeepMetaHandles, learning deformation metahandles of 3D meshes with Biharmonic coordinates. This work is by Minghua Liu, Minhyuk, Radomir Mech, and Hao Su. Generating 3D meshes is challenging, due to the irregularity of mesh data structures. Instead of generating a mesh from scratch, recent work create new shapes by leveraging deformation handles. Common deformation handles include template meshes, bounding boxes, control points, and enclosed cages. However, existing handles typically do not have semantic meanings. There will be lots of implausible deformations if we randomly move the handles. What we want are more intuitive handles, which provide us meaningful deformation directions, and factorize all plausible deformations of a shape. In this work, we propose DeepMetaHandles, a 3D conditional generative model based on mesh deformation. Taking a collection of 3D meshes of a category and their control points handles as input, our method learns a set of metahandles for each shape. For example, this figure shows the learned metahandles of a chair. Although we do not take any semantic annotations as input, each learned metahandle corresponds to an intuitive deformation. For instance, we have a metahandle adjusting the thickness of the chair seat, a metahandle changing the height of the armrests, and a metahandle bending the chair back. As shown in the figure, the learned metahandles are disentangled and factorize all the plausible deformations of the chair. We utilize control points as the deformation handles. Specifically, given a mesh, we first sample C control points by furthest point sampling. We propagate the control points translations to the entire mesh by leveraging the linear Biharmonic coordinates. We then propose to learn a small number of metahandles for the shape. Each metahandle Mi is represented as the combination of the offsets over the C control points. In contrast to a single control point that mainly affects a local region of the mesh, each metahandle is expected to provide a more intuitive deformation. We then use the linear combination of the metahandles to represent a deformation, where the vector A is the linear combination coefficients. We can also interpret it as a latent code, describing the deformation. However, unlike the implicit latent code by most existing works, our latent code can be explicitly decoded to a deformation. We utilize a small number of metahandles to cover all plausible deformations, so that the metahandles are required to discover the correlations of the control points and the underlying properties of the shape structure. How do we learn the metahandles? We learn the metahandles in an unsupervised fashion, without taking semantic annotations or correspondences as input or supervision. To avoid learning zero deformation as metahandles, we employ a target-fitting training strategy. As shown in the figure, our method mainly includes two modules, MetaHandleNet and DeformNet. Taking a pair of randomly sampled shapes as input, the MetaHandleNet will first predict a set of metahandles for the source shape. Based on the predicted metahandles, the DeformNet will then predict a latent code to deform the source shape and match the target shape. For the loss functions, we utilize chamfer distance to encourage the deformed source shape to match the given target shape. We use geometric regularizations and adversarial regularization to ensure any sampled deformation is plausible. Moreover, we employ disentanglement regularizations to encourage the learned metahandles to be disentangled and factorize all plausible deformations. Let's take a look at more results of our learned metahandles. As shown in the figure, our learned metahandles are consistent across different shapes. Despite geometry details and even global structures being different, each metahandle can find corresponding regions across various shapes and predict similar deformations, which is very interesting. The learned metahandles are also disentangled. They factorize all plausible deformations of the shapes, which enables many downstream applications. We have already released our code and also provide a web-based demo to play with the MetaHandles.